All right, so we got a big bad word problem for us here. It's really all about this formula. Anyways, so a baseball leaves a bat with an initial speed of 30 meters per second, clears the fence 90.5 meters away. The height of the fence is the same height as the initial height of the batted ball. If the distance the ball traveled is given by this this formula here, where 9.8 is in meters per second squared, find the interval of possible launch angles of the ball. All right, so we want to plug everything in here. 90.5 meters, of course, is our distance. This equals our initial velocity, 30 meters per second squared, times sine of 2 times our angle over 9.8. Now, before we get into this problem, I just want us to realize, okay, so we're dealing with real life here. We're going to be thinking in terms of degrees. All right, just because we're thinking about this, the situation that we're in right here, this formula is written for degrees. We have distance, initial velocity, 9.8 meters per second. We're not going for those exact measures of radians. This is set up to be used in degrees. So if we just simplify this down, multiply both sides by 9.8, divide by 900, we get as a fraction 8869 over 9,000 equals sine of 2 theta. Okay, we should be able to multiply the other side by 9.8, divide by 900, and as a nice reduced fraction, the calculator gives it to me. We get that. That's sine of 2 theta. I didn't get rid of that 2. All right, that 2 is stuck inside of our sine function. So if we want to find sine, make sure your calculator's in degrees. Like I said, we're dealing with degrees, not radians. Take the inverse sine of both sides. The inverse sine of this fraction gives me 80.21-ish, 80.21-ish degrees equals 2 times our theta. Of course, when you divide both sides by 2, when we divide that by 2, we get about 40.1-ish degrees equals theta. So think about what's going on here. There's an interval of possible launch angles. There's not just one angle that you could hit it at. There's not one perfect angle. There's a range of angles. So let's say this right here, what looks like this is the least 40.1 degrees. Well, there's an angle that would be too much. Imagine if you hit it too high initially. It's not going to go the far enough distance to clear that fence. So there is a greatest angle. So we have to find the whole range there. And remember back to when we were dealing with like side angle and things like that, we really started to kind of discover that the sine of a value and the sine of that value's supplement are actually the same output. Well, in this case, because we are multiplying by 2 times theta, well, we would have to divide both sides by 2. It's not going to be the supplement, it's going to be the complement. So we want to know what value adds to 40.1 to get us 90 degrees. And that is also 49.9. This will give us also the same output. So the largest angle we could have would be 49.9 degrees. It's got to have that sweet spot between 40.1 degrees and 49.9. The interval of possible launch angles, 40.1 degrees to 49.9 degrees. Now, double check that. Don't just take my word for it. Let's plug that back in. Sine of 2 pi, so first of all, 8869 over 9,000 as a decimal is about 0.9854. Well, if I do sine of 2 times 40.1, sine of 2 times 40.1, notice that, I'll let you see it right there in the calculator, gives me about the same value, 0.9854 when I did sine of 2 times 40.1. Well, let's double check the other value. 49.9 sine of 2 times 49.9. Look at that, it gives me the same output. So that's because we were multiplying it by 2. It's not just a straight theta. We're doubling that. If we double 40.1 and we double 49.9, those two values are supplements. These two values, though, are complements. So here's the two values that would get us the distance we need to clear that fence.